Can you use an F statistic to test hypotheses about the mean? Can you use an F test to test hypotheses about means?
Yeah.
In what context? Right, same population. So Van says that if we have two groups of data and we want to know whether or not they came from the same population, we could test hypotheses about whether or not the means in the two groups are the same. And that's commonly referred to as what? Van said that if we dug up some old bones in Australia and we measured the length of the femur, the thigh bone in these skeletons, and then we dug up in, where did they dig up this new species of Homo erectus that they think they found in South Asia, Southeast Asia? In Borneo or Malaysia, they found another skeleton down north of Australia somewhere, a set of skeletons, and they think it's part of the new species in the human evolutionary line. And the reason they think that is because they're smaller in stature, even though there's evidence from the bones that it was an adult skeleton. So from these new ones, they also measured the length of the femur. And Van tells us that we can compare the mean femur length from the population of bones that we got out of Australia and the mean femur length that we got from, say, Malaysia. And by comparing the sample means, you can decide whether or not they were belong from the same population. And what's the testing procedure that we use to do that? What's the name of it?
Yeah,
The question was, we want to test the null hypothesis that two means are equal. What's the generic term for that kind of testing framework? Right. Analysis of variance. Analysis ANOVA. Analysis of variance.
How does that, I thought that whole story in various people started with ratios and
Oh yeah, somebody told us that the small sample tests that your customer is using are Z, T, chi-square, and F.
Yeah.
And so I asked, what kinds of hypotheses would you test with Z and T? And somebody said the population mean. And I said, what kind of hypothesis would you test with chi-square? And somebody suggested we might test a hypothesis about population variance. And the test statistic that we could use was the sample variance. And we know that that's chi-square. And then I said, well, the F is another test statistic. And I said, could you use an F test to test a hypothesis about means? And Bob said, well, that was the answer he gave me. He said you could use an F. And Jeremy says that testing for the equality of means is an F test and it's usually understood to be analysis of variance. Well, if the F is the ratio of two chi-squares, right, why is it that we're using the F to test a hypothesis about means instead of testing a hypothesis about variances? Don't you find that a little confusing?
because it's mean is plural, like the variance, you can have a mean of the different variance.
Ooh, you are one tricky person. I suppose in a sense you're right, but I don't know that you're right for the right reason. The idea behind analysis of variance is that in analysis of variance, we're saying that the mean bone length from Australia is the same as the mean bone length from Malaysia because the skeletons all come from the same population. Therefore, because they all come from the same population, the variance should be the same for both places. So the presumption in analysis of variance is that regardless of whether or not the populations are different, the variances are the same in the two populations. And so the question that we ask, the way we pose the question is, suppose that the skeleton size in Australia really is different from the skeleton size in Malaysia. It really is. Well, where would we expect to see that happen? Well, suppose that we impose the restriction that the means are the same and compute a variance, and then we compute two variances when we relax the restriction. And then we're comparing the variances, although we're testing a hypothesis about the mean. Go ahead, you're trying to get your hand in there.
I was going to go back to something.
Now I completely wiped it out of your brain. Relax the restriction? Remember, in analysis of variance, you compute the group means, and then you compute the group variances, and you compute the grand mean and the grand variance. And in the numerator, you put the sum of the group variances, and in the denominator, you put the grand, the other way around. In the numerator, you have the grand variance, and in the denominator, you put the sum of the two group variances, everything divided by its appropriate degree of freedom. So your test about the means is being based on the because you incorrectly imposed the restriction that the people from Malaysia were the same as the people from Australia. This half the room is from Malaysia, it's corpses from Malaysia, and this half the room is corpses from Australia. And the thinking is that people from Australia and people from Malaysia descended from a common ancestor, and that the two populations aren't separate species. They might be separate species, but because they descended from the same ancestor, the variance in bone length is the same in both places. But because they're different species, the bone length itself is different, the average bone length. If, in our computation of the sample variance, we require that we compute a grand mean across everybody, what we're doing is imposing a restriction that the mean bone length is the same in both subpopulations. And so our estimate of the variance is going to be wrong. On the other hand, if I compute a variance for this group and a variance from this group, they're going to be different because they're different species. And so what I'm doing is comparing that unrestricted sum of variances against the grand variance, if you will. So if there's a big difference between a grand variance and the sum of the two subpopulation variances, then I reject the hypothesis that everybody came from the same population.
But I have a question.
Oh, right.
So do you need to do an test for this? It seems like this.
No, probably in basic statistics when you were asked to compare the equality of means, you learned to do a t-test.
Yeah.
But remember...
Is that test better?
Oh, that's a good question. We'll come back to that. Remember that the square of a t-statistic is an f, with 1 degree of freedom in the numerator and n minus 1 in the denominator, say. And so there's an equivalence between the ANOVA test and doing a t-test on equality of means. Probably in basic statistics nobody pointed that out to you. But the two tests are the same. But Laura's next question was, which test is better, that F or that T? Which raises the question of the power of a test. The notion of the power of a test is how able you are to discriminate between your null hypothesis and the truth. There was our power curve there. And Lacey told us that as your sample size gets large, the power curve becomes steeper, tighter around the vertical axis as the sample size gets large, because a bigger sample enables us to discriminate between the null and the truth. However, we're not going to be able to talk about that for quite some time. The traditional test of hypothesis that we've done thus far is based on squared error loss, where, I know, let's do it, something that you know. A week or two ago, I suggested that the mean and the median were both measures of central tendency. So they're two different estimators for the same thing. You could use the sample mean as a test statistic, and you know that the distribution of the corresponding test statistic has a t. Or you could use the median as a test statistic. And then the distribution is a little bit more complicated to do it. To figure out the median is an ordered statistic, and so you can answer the usual statistical question. Which is more the more powerful test, the median or the mean? The mean is the more powerful test. And using ordered statistics, you could generate the power curve for the median. So if this is the power curve for x bar, then the power curve for the median looks like that. So the sample mean is the t-statistic is the uniformly more powerful test statistic. Yeah.
Because it assumes the normal distribution, whereas the non-parametric assumes no distribution of the median into the ranks.
No, there's a distribution that otherwise ranks. And you can figure out the distribution of the ordered statistic, assuming normality. And even if you assume normality of the underlying random variables, the mean is still more powerful because it has everywhere for any sample size that has a smaller variance. And so we know that the power curve for the median as a test statistic lies below the power curve for the mean. You're still using that. Testing the difference, testing the hypothesis that the difference is a certain number. It's just shifting the mean, where you center the distribution.
So getting back to your original point here, there's no difference in power between the t-test and the ANOVA.
Right.
They're the same thing. It's just that you use t-test for comparing two, whereas ANOVA is multiple comparison.
I could construct a t-statistic for any number of means.
Yeah.
There's nothing special about that.
But it doesn't have the corrective properties for multiple comparison.
Sure it does. Yeah, because the two statistics are the same. One is a transforming